Hello friends, welcome back. In this video, we will discuss about IS-IS adjacency process. So we will discuss how neighbors are discovered and maintained. So we will cover why do we need adjacency in the first place, and then we will check the various adjacency parameters, what must match and what does not need to match between two IS-IS speakers to establish adjacency. And then we will go over a very important topic, which is the IS-IS Adjacency State Machine. And we will discuss the three states that IS-IS routers go through when they establish the adjacency. And then we will go over some verification commands and some of the reasons why two IS-IS speaking routers do not establish adjacencies. So without further ado, let's jump straight into the topic. So like any other routing protocol, be it OSPF, BGP, RIP, IS-IS identify neighbors by sending and receiving hello packets. They are called IIH or intermediate system to intermediate system hello PDUs. And that's how they find other IS-IS speaking routers on a circuit. And when I say circuit, it could be a point-to-point interface or broadcast interface. So in IS-IS, like previously discussed, we only have two network types. We have the point-to-point network type, or we have the broadcast network type, or multi-access network type. And then they verify the compatibility between the routers by verifying the various parameters like authentication area ID in case of an L1 or a level 1 adjacency. And then once the parameters have been verified to be consistent or compatible, only after that a full adjacency is established and the two ISI speaking routers can now exchange LSPs and synchronize their link state databases and run the SPF algorithm to derive the shortest path tree. So let's check what are some of the adjacency rules. So what must match or what does not need to match for two ISI speaking routers to establish adjacency. So the router levels must be compatible. When I say router levels must be compatible, it's specifically for L1 router. So for an L1 ISIS router to establish an L1 adjacency, it must be speaking to another router in the same area. So L1 neighbors require matching area address and the system ID must be unique in the area as well. So for example, if we configure R1 to have the router ID of quad 0 and 0001, that system ID cannot be used on another router in that ISIS domain. And there are some interface compatibility which must match. So if we are using hello authentication, the authentication parameters must match. The MTU values must match as well. So as ISIS is a link state routing protocol, when they exchange their LSPs, one of the parameters that must match is the MTU value on that interface. And in regards to the timers, it is important that we note that the timer values do not need to match in ISIS the same way they do have to match in OSPF. So as long as we receive IIH or ISIS hello messages from the neighbor before the hold timer expires, that's when the router simply resets the hold timer. So the bottom line is that the hello timer on the two ISIS speaking routers do not need to match, and it's an advertised parameter, not something that is negotiated. So going over the various packets that get sent between ISI speaking routers to establish the adjacency, we have the LAN 1 IIH packets. They get sent to all level 1 IS MAC address, which is the value that you see on the screen here. And then we have the level 2 LAN hellos, and they get sent to the well-known MAC address ending with 0015. And then we have the point-to-point IIH, So on point-to-point circuits, there is only one type of IIH that gets sent, and they get sent to the MAC address. That's the value ending with 0005. So let's talk about the IS to IS routing protocol state machine. So unlike OSPF, where we have various states, like we start from down, we go attempt in case of a broadcast network type, then we have the init, two-way, xstart, exchange, loading, full. But with ISIS, we only have three states that an ISIS router has to go through before it establishes adjacency. So the states are down, init, and up. So let's go over these states one at a time. So with down state, it's the initial state where the adjacency process starts. At the down state, no neighbor has been discovered yet. So the router sends its hello messages or IIH, but it hasn't received any neighbor hellos. So that's when the router stays in the down state. The next state is the init state. So in this state, a hello was received from the neighbor. So we know the neighbor's interface address, its local circuit ID, but the local router does not know, or it cannot be sure that the remote neighbor has received its hello message. So a hello was received, so the neighbor is known, but bidirectional confirmation is not complete yet. So the local ISIS router is not sure if the remote ISIS router has received its IIH packet yet. And the third state is the up state. So the ISIS router transitions to the up state once it receives a hello packet with its own router ID in the hello message. So now let's go over the three-way flow of the adjacency process for point-to-point network type. So if we have two routers, router A and router B, so in step one, router A sends IIH towards the MAC address that we saw on the previous slide. So this is for a point-to-point network type. So we will use the well-known MAC address ending with 0005. So currently router A is in down state, as that is the initial state, and router B now receives the IIH from router A, creates the neighbor entry. It then moves to the init state and replies with its own IIH towards router A. And in that IIH, router B can now include the system ID for router A, as it has already received an IIH from router A. So when router B sends an IIH, it does include router A's system ID in that hello message. So in step 3, router A sees or receives router B's IIH, and it carries the expected reference to router A. So router A now knows that router B must have received its hello message, and it can now move the session state to bidirectional or the up state. So like it says in step 4, once each side sees the expected neighbor information, the adjacency is promoted to up state. So once router A sees its system ID in the IIH it receives from router B, the next hello message that it sends will have the adjacency state as up, and with that, router B will know that router A has received its hello message, and both sides can now reach the up state. So let's check the behavior of neighbor discovery when it comes to a broadcast network type or a LAN network. So as we know that Cisco routers runs both level 1 and level 2 of IS-IS at the same time. So on a LAN network, we send out both L1 and L2 hello messages at the same time. So like it says, a single Ethernet circuit can maintain separate control plane state for each level. So two levels mean two levels of IS-IS database, one for level 1 and one for level 2. And one of the very important distinctions between a hello message sent on a point-to-point interface as compared to an interface running broadcast network type, there is the process of a DIS election on a broadcast network type. So based on the IS-IS priority on that interface, the routers in a broadcast network type will elect a DIS or a designated IS to reduce the database synchronization complexity, and it's the responsibility of the DIS to send CSNPs or complete sequence number PDUs every 10 seconds to ensure that all the routers in the broadcast network have an identical copy of the LSDB. So the DIS election can be compared to, or it is analogous to, the DR process or the DR election in OSPF. However, there is no backup DIS in case of ISIS, like we have a backup designated router in OSPF. So like we discussed, there is the DIS election process that occurs on a LAN segment. It's done to reduce the full mesh requirement and to ensure synchronization on a broadcast network type. And like we discussed earlier, we use priority to elect the DIS on a LAN segment, and the interface with the highest priority is elected as the DIS, but if in case of a tie, the highest MAC address becomes the tiebreaker. And continuing our discussion on the timers, so each interface configured to run IS-IS sends IIH packets every hello interval, and there is this concept of hello multiplier, which is the hold timer. So if the interface does not receive a hello message from the neighbor in that hold timer, the adjacency ages out and the neighbor is removed from the IS-IS neighbor table. And like previously discussed, unlike OSPF, IS-IS hello timer do not have to be identical across neighbors for the adjacency to work. As soon as a new hello message is received, the hold timer gets reset. So going over some operational commands. So when troubleshooting IS-IS, show IS-IS neighbor is a very good verification command to check the established neighbor on the router. And then we can also run show CLNS neighbor detail to get more detail about the neighbor. And just like we check the database in OSPF, we can also run show IS-IS database with the detail switch to get more detailed information about the database on an IS-IS router. And another important command is show IS-IS protocol. It shows the interfaces on the current router which has IS-IS enabled, and also the metric type that is currently supported on the local router. So we will go over these commands when we get into the lab section and discussing about some common failures on why two IS-IS routers would not form adjacency. One of the most common reason is the area or level mismatch. So there are certain rules when it comes to adjacency between two IS-IS running routers. For example, a level 1 router can only establish neighborship with another level 1 router if the area ID matches on these two routers. It can also establish adjacency with another router running level 1, level 2 IS type, but the area ID needs to match. So in summary, L1 can only speak with another L1 if the area matches. L1 can establish adjacency with another L1, L2 router. Again, the area must match. So if a router is running L1 level type and the neighbor is running L2 IS type, and even if the area matches, they won't establish the IS-IS adjacency. And like we discussed earlier, if a router is running L1, L2 IS type and the neighbor is also running L1, L2, they will form two pairings i.e. L1 and L2, as long as the area matches. If they are in different areas, they will only form an L2 adjacency. And if we have level 1, level 2 on one side and level 2 only on the other side, they will only establish a level 2 adjacency. And with level 2 and level 2, they will only have an L2 adjacency. So this is a summary of the resulting adjacency that will be established given the various combinations of levels running in an IS-IS network. And going over the packet flow and a practical troubleshooting sequence, a good starting point is to make sure there is layer 3 reachability between the routers and the MTU size match at both ends of the IS-IS peering. And we can also check interface details confirming the MTU size, the circuit type, and the adjacency counts. And then if we can run some debugs and capture the IIH packets or the hello messages. So the whole idea behind getting to the adjacency state is to make sure that the LSTBs are synchronized. And if there are issues with adjacency, we won't have identical LSTBs, which will result in failure in SPF-based route computation. And these are the parameters that need to be checked in case of most failures. And like we discussed, there are three core states in the IS-IS adjacency state machine. We have the down state, we have the init state, and then we have the up state. We also have three primary MAC groups. So we had the point-to-point MAC address. We have the level 1 MAC address for a broadcast network type, and then we have the level 2 MAC address for a broadcast network type. So let's go over our lab where we have a simple topology to demonstrate what we discussed today. So we have three routers, R1, R2, and R3, with R1 and R2 in area 490012 and R3 configured to be in area 49.0003. So I have configured the IPs on the routers to save some time, and then we will go over the IS-IS neighborship and we will check the packet captures. So let's check the adjacency establishment step by step on R1 and R2. So on both R1 and R2, I've configured VLAN 10, and the IP that I'm using on R1 is 10.1.2.1, with the IP on R2 being 10.1.2.2, and the link between R1 and R2, that's a trunk link carrying only VLAN 10 for now. So if we do a show spanning tree for VLAN 10, so it is in forwarding state on gig 01. So let's do a spanning tree on R2 as well. So we see that it is spanned, or it is in forwarding state on interface gig 02. So let's do a ping between R1 and R2. Yeah, we can ping between the two devices. So let's check the router IS-IS configuration on R1. So I changed the NET value on R1 to 49.0012 as the area ID, and the system ID is quad 0 quad 0 0001, and the end cell being 00. So let's check the same on R2. So we currently have an area ID of 49.0001 on R2. So let's change that to 49.0012 so we can establish an L1 adjacency between R1 and R2. So if we do a show run section router on R2 again, we see that the net ID on R2 has been set to 49.0012 as the area ID. Okay, so let's check the IS-IS neighbor on R1. So currently it's in downstate, and unlike OSPF where we see the downstate where the router explicitly says neighbor is in downstate, in IS-IS for a neighbor that's in downstate there is no output at all. So let's do the same on R2, and interestingly, on R2, we see that the neighbor is stuck in init state. So what we did here is that we created an access list called block IS-IS, and we denied the two the two well-known MAC address that broadcast network type uses. So we denied these two MAC address and we permitted all the others. And then we applied this access list on interface gig01 on R1. So it is currently sending IIH packets, but it's not receiving anything as we applied the access list on interface gig01. So if we run a debug on R1, so let's say if we do a debug IS-IS adjacency packets like we discussed earlier, so we will see that we are sending both level 1 and level 2 LAN IIH packets, and we will do the same on R2 as well. So like we see, we are sending L1 hellos and L2 hellos on VLAN 10 because that's the interface configured to run IS-IS, and if we can also check that using show IS-IS protocol like we discussed earlier. So if we check the section which says interface supported by IS-IS, it says VLAN 10 and loopback 0. And if you check the debug output on R2, we see that it's sending IIH packets and it's also receiving them because the access list on R1 is in the inbound direction. So it's not stopping R1 from sending hello messages, it's only stopping it from receiving them. So like we see, it's sending the IIH packets. So let's have a look at the packet capture. So we will do a capture between R1 and R2 on this link, and then let's filter it to only show IS-IS hello messages. So let's check an L1 hello message from R1. So we know this is R1 based on the sender system ID. So the system ID that we configured for R1 is the one ending with 0001, and this is an L1 hello like we see on the screen. It has a numeric identifier of 15 and it says period type is L1 hello, and we have both L1 and L2 circuit type on interface gig01 on R1, and we can verify that with the command show CLNS interface VLAN 10. We see that it has a circuit type of level 1-2, and currently there is no DR ID or designated intermediate system on this interface as the two routers haven't established the IS-IS adjacency and they haven't gone as far as electing a DIS. And like we discussed earlier, the interface priority on an IS-IS interface running broadcast network type is the value of 64 for both level 1 and level 2, and the default metric for an interface running IS-IS is a value of 10. So let's have a look at the Wireshark capture. So this is a capture of a hello message sent by R1. So let's check the reverse as well. So let's check a hello message sent by R2. So this is a level 1 hello that sent by R2, and we can say that going by the system ID. So this is a level 1 hello like we see here. So one of the important differences between these two hello packet is the IS neighbor field, which is missing in case of the hello sent by R1, but R2 has already received a hello from R1. So when it sends a hello message towards R1 or to this well-known MAC address, which is 0014, that's the well-known MAC address R2 is sending the hello to, and this is the well-known MAC address for a level 1 peering. So it includes the MAC address of VLAN 10 on R1. So if we check the interface VLAN 10 on R1, we see this value here, 0C, 0E, AC32, 800A, and that's the same value that R2 sends as part of the IS neighbor field. So this confirms that R2 has received a hello from R1. And let's say if we remove the access list that we have applied on R1, show run interface gig 0/1. So we have applied the MAC access group command on R1. And let's say if we remove it, so let's stop the debugging on R1. So let's go back to interface gig01. Let's remove the MAC access group command on that interface. And now let's run the show IS-IS neighbor command again. So they have now gone to form adjacency. And let's now compare one of the hello message that R1 sends. So this is another hello message that R1 has sent. So it now includes R2's neighbor interface MAC address as part of its hello message. And when R2 receives this hello message, it now knows that R1 has seen its hello message, and both neighbor can now get into the upstate and start exchanging LSPs. So let's stop the debug on R2 as well, and let's check the IS-IS database on both R1 and R2. So R1 and R2 have synchronized their database, and like previously discussed, on broadcast network type, there will be an election for a designated IS or DIS, and we can check that using the command show CLNS interface VLAN 10. And for this segment, R2 is the DR, and let's do the same on R2. And like we discussed in the theory, R2 creates two entries for the local router, one for itself and one on behalf of the pseudonode, as it has been elected as the DIS. So let's do a show CLNS interface VLAN 10. So we can see that R2 has been elected as the DR or DIS. And let's check why has R2 been elected when both R1 and R2 have the same priority of 64 on VLAN 10. So one of the ways to check that is by using the command show IS-IS topology. It shows the neighbor's SNPA or the MAC address configured on the interface which is connected on that segment. So from R1's point of view, R2 is its neighbor with a metric of 10. So next up is R2, which is what we expect. And then it's configured on VLAN 10, and R2's MAC address on that VLAN is the value that you see in the screen highlighted. So let's verify that. Show interface VLAN 10 on R2. So we see OC7D0396800A. Yeah, that's exactly what we see on R2 as well. So this is the SNPA or subnetwork point of attachment. So that's the point using which a router connects to that LAN segment. So R2 connects to this LAN segment using this MAC address. So that's what the SNPA represents or stand for. And R2's SNPA has a higher value as compared to R1's SNPA. So OC7 will prevail over OC0. So yeah, that's the reason R2 has been elected the DIS on this segment for both levels 1 and level 2, because we haven't made any level specific changes on these routers. So this is the DIS election process. Hope that's clear to you now. And let's say if we change the network type to point on both R1 and R2, so the network types do not match. So they have dropped the adjacency, and I'm going to run the debug command on R2 again. So yeah, as you can see on the screen, it has received a point-to-point IIH on multi-point interface, and it is ignoring the IIH from R1. So let's go to R2, and so let's go to interface VLAN 10. IS-IS network is point-to-point. And as we see on the screen, R1 has established a peering with R2, and the type of peering is both level 1 and level 2. So it's only one peering between the two neighbors. And let's have a quick look at the packet capture and look at one of the hello messages that has been sent between R1 and R2 after we have changed the network type. So this is a hello message sent by R1 going by the system ID again. And one of the noticeable differences is the PDU type. It has changed to P2P hello with an ID of 17. And point-to-point network type, when we send the hello message, we include the adjacency state. Here we see that the adjacency state is up, and we also include the neighbor system ID. So when R2 receives this hello, that serves as a confirmation to R2 that R1 has received its hello message, and that's the reason R1 has changed the adjacency state to up. So this is one of the initial hello message that R1 sent towards R2. Yeah, we see the PDU type is point-to-point hello. We see the adjacency state is down, and like we discussed in down state, the local router has not received any hello messages from its neighbor, so it cannot include the neighbor's router ID in its hello message that it sends. So here we see that R2 has sent a hello message. It sends the adjacency state as down, and when R1 receives this hello from R2, it changed the adjacency state to initializing, and it also included the system ID of R2 in the hello message like we see in the screen. And here we have a hello message from R2 with an adjacency state of initializing and a neighbor, and it does include R1's system ID in the adjacency state along with its local circuit ID like we checked earlier. Now that R1 has received a hello message from R2, it changed the adjacency state to up, and it also includes the neighbor system ID. And now when R2 receives this hello message with the adjacency state as up, it also changes the adjacency state in the hello message that it generates and sends towards R1. So like we see, there is some differences between the adjacency mechanism between broadcast and point-to-point network type. So I hope the process of IS-IS adjacency both for broadcast and point-to-point network type is clear. So friends, that's it for this video. In our upcoming sessions, we will discuss about the various levels of authentication that we use in IS-IS routing protocol. So friends, I hope you liked the content of this video, and if you did like it, please hit the like button and please share this video with your friends and colleagues. And if you are new to this channel, please hit the subscribe button. Yeah, and until next time, thank you very much for your time. We'll see you soon. Thank you, guys.